This is the 17th session of the part 1 of this series of lecture. And in this session, I want to discuss a new algorithm which I haven't discussed so far, called concentration of frequency and the time, or ConceFT. This is the paper that you can check if you are interested in details. So recall the first fact. The fact is, synchrosqueezing is robust to noise, which we discussed in session 6. So recall this theory and this result, this example. I give you a clean signal, and this is the noisy signal. And if you remember, if I show you the synchrosqueezing transform of the clean data and the noisy data, you will see that they are quite similar. They're quite similar, except some background scenes caused by noise. But overall, they are very close. And that is the result of second-order synchrosqueezing, which gives you sharper results, but it is also robust to noise. And as I mentioned in session 6, the associated theory is still open, and we hope to have something quick, soon. And well, whatever, when it's ready, it is ready. However, when noise is big, it is still challenging. It's still challenging. For example, I give you two signals, two components, okay, the instantaneous frequency and amplitude. This is the clean data. But this time, I add a big noise, and the noise is complicated with ARMA 11, and the innovation process is T4, student T4. So the signal to noise ratio is almost minus 1 dB, which is considered very, very small. And this is the noisy data. And now let's take a look. This is a synchrosqueezing transform of the original signal, clean data. You can see, okay, that is okay, not too bad. But if you look at the synchrosqueezing transform of the noisy data, then you see, hey, you can still see two curves, right? But background becomes very, very strong. Background becomes very, very strong. And you can see what are they, right? A lot of structures. It is maybe not that easy for us to determine what's going on. And this is the problem we have discussed before, right? When two components have close frequency, there will be some frequency interference, and this is a boundary effect. So there are many issues. So how to handle it? A very traditional idea is called multitapering, which is an algorithm or a technique trying to reduce the variance of estimating the power spectrum. So it's called, was originally proposed in 1982, I remember, 1982, by Thompson. And the basic idea is very simple. To stabilize the periodogram, in particular to reduce the variance of the periodogram, what we do is we take multiple windows, and those windows are orthogonal, and we evaluate the periodogram with those windows tapering, and then we do an average. And you will see that is the kind of example. If you have the original periodogram, which is very fluctuating, but if you take 4 windows, then you can get something less fluctuating. I will not go into detail of the traditional multi-taper algorithm, but if you have interest, that is very famous textbook with details. What we will do is actually generalize this idea to the time frequency domain, to the time frequency analysis. And the idea was first introduced in 1998. There's no year here, sorry. But whatever, that is the paper by Patrick Flanagan. The idea is very simple. You take different windows. For example, this is the Hermite window, second Hermite window, third Hermite window. And with different windows, you evaluate synchrosqueezing transform. And once you get those synchrosqueezing transforms, you can see that, okay, the signal parts are similar, although, well, maybe not perfect, but they are similar in some sense. But if you take a look at the noisy part are more kind of different. So if you take this into account and you do average it, then this is the result, which is actually much better than when you have only used one window, isn't it? It's much better. You can see two curves, and the background noise is less strong. And the basic idea is very simple. You just say, hey, the windows are orthogonal, so after evaluating the time frequency representation, the noise will be independent because the windows are orthogonal. And then, because of the independence, if you take average, you can suppress the noise impact. But the signal part, because the windows are still concentrated and nice, so the signal parts will be kind of fixed. And that is the basic idea, leading to this improved time frequency representation. Okay, that sounds like a good idea and already solved the problem. However, it doesn't. Why not? Because we cannot have as many windows that are orthogonal and concentrated in the time and frequency as possible. Well, as we wish, we cannot. We can only have, if we want to have very concentrated window in the time frequency domain, then we only have a few windows. But if you want to have many windows, then the windows will spread everywhere in the time frequency domain, and that is kind of the Nyquist rate idea in the time frequency analysis. That is, sorry, it is not possible to get as many windows as you wish. As many good windows as you wish. You just cannot achieve it. Okay, and the basic idea is the following, and quantify it in the following way. So we have some kind of concentration in the time frequency domain. Lambda is the shape in the time frequency domain. For example, this ellipsoid is one possible shape. This circle is another possible shape. You can even have this tilt ellipsoid and so on. They are all potential shape, lambda. And then we have r, which is the size. For example, this is the circle, and you can have different sizes. And once you have shape and the size, then you can try to evaluate the concentration in the time and frequency. This is the operator that try to concentrate the energy in both time and the frequency axis, but the concentration will be over the region that is quantified by the shape and the size. And if we view this operator as a linear operator and we evaluate its eigenspectrum, then you can see something very interesting. The eigenvalues will drop quickly after some time, after some indices. So usually if you focus on the circle, for example circle, then you will get Hermite windows, and usually 6, 10 maximum. We can get 6 or 10. So in the end, if you try the multi-tapering idea, you will only get 6 or 10 copies of independent noises. And well, you just cannot get too much. You cannot go too far. And a similar idea also holds for continuous wave transform, and we will discuss it in later session. Okay, and there will be some of these kind of patterns. And this is the literature, the paper you can consult if you have interest. It is maybe 1988, very early paper. So the idea we want is the following. We want to have as many as possible good windows. That is what we want. But as I told you, because of this increase rate fact, we cannot have as many good windows as we want. So can we do something different? Yep. So we try the following. Suppose we take 3 good windows. 3 good windows. H1, H2, and H3. Okay? And these 3 windows are very, very highly well concentrated in the time frequency domain. So they are good. But we only have 3. But how about if we just take any possible linear combinations? That is, we view H1, H2, and H3 as 3 points on the sphere. And then we try to generate as many windows as possible by taking all the points on the sphere. Can we do it? If we can, well, come on, we can generate as many good windows as we want, right? Although those windows, unfortunately, those windows are dependent. They are dependent. But, well, as you will see, this idea still works. And the algorithm, resulting algorithm is called concentration of frequency and time, ConceFT. So what you do is, you have the noisy signal, and you take the first window. Okay, you have 3 windows, right? H1, H2, H3, but we just take some random combination, and this is the first window. You see this is not either not H1, H2, or H3. You see that this is not symmetric. And this is the result, right? Good. We can have yet another window, and this is the time frequency representation by synchrosqueezing. Good. Now we can continue to do as many as we wish, and we average them. What's wrong with this? And this is the average. If you pay attention, it is not bad, right? You can get the 2 curves. They are associated with the ground truth. That will be the ground truth. And the background noise is actually much weaker. Much weaker. So you somehow achieved the denoising mission. So noise actually become more independent, although the windows are dependent. And because of this more independence or less dependence property, the averaging comes to play and help to reduce the noise. So actually we leverage the nonlinearity of synchrosqueezing. Because synchrosqueezing itself is a very nonlinear operator. And so although the windows or noise are dependent, they're linearly dependent. But this nonlinear operator will break this linear dependence so that you can leverage the independence of noise to get a cancellation. And this is a comparison. Okay? The synchrosqueezing transform of the clean data, and this is the noisy data. And this is the multi-tapering of the noisy signal with 6 windows. You can see it is much better already, but still not perfect. And, and this is a concept of the noisy data and with the ground truth superimposed on it. So you can see this is a much better improvement upon the traditional multi-tapering. And the more interesting thing is, if you just take the clean data and run multi-tapering, if you compare these 2 figures, what do you see? You see something very interesting, isn't it? First, the boundary effect disappears. The interference seems to be eliminated. Isn't it? Isn't it nice? Yes, right? This gives us something some very interesting results. And we'll talk about this theoretical support in the later session. And at this moment, if you have interest, you can take this paper for some small details, but there are a lot more to discuss. I want to show you applications about how well and why ConceFT can help. So first, let's recall the ECG-derived respiratory signal, EDR. It is very simple. You recall this is ECG signal. We have instantaneous heart rate, but we also have the amplitude of our peaks. That is called ECG-derived respiratory signal, or EDR. Why? Because when you breathe and when you inhale and exhale, the impedance inside the chest changes, so that the amplitude, the size of the the QRS complexes change. Okay, so this is the simultaneously recorded airflow signal and the ECG signal derived respiratory signal. So you can see two. And this is the signal recorded during the first reaction in the surgery, in the end of the surgery. So this is before first reaction, and that is after the first reaction. I want to show you how the signals look like and how ConceFT gives you. And you can zoom in. Now you can see quite nicely synchronized, right? So you get the EDR signal. Nice. And this is during the first reaction. So you can see the airflow signal is quite chaotic in between, and the EDR is also very chaotic. But before and after, you can see very nice synchronization. Okay. And this is the time frequency representation determined by ConceFT. You can see that the fundamental frequency is recovered. Okay, and this is the simultaneously recorded airflow signal. You can see the fundamental component, okay, and the multipulse, very nice, isn't it? And you have some dynamics. And in the EDR signal, you can almost only get the fundamental component and a bit second harmonic. And what does it tell us? It tells us that the so-called respiratory signal you get from the ECG signal has a different oscillatory pattern compared with the airflow signal. In a sense, ECG signal can be viewed as a sensor to detect the respiration. But this detection is different from the nasal cannula or pressure-based flow signal sensor. Now we want to apply it to see to the heart rate variability analysis and see anesthesia depth. Okay, so again, this is the instantaneous heart rate signal, and we have showed that we have said that it is very non-stationary, and the traditional methods may not be a very good idea. And we also mentioned surgery and anesthesia, right? If you have EEG signal, brainwave, it mainly, if it is on the beats, it mainly will detect the frontal lobe behavior, but heart rate variability will give us some subcortical activity. So this is the instantaneous heart rate recorded during the first reaction. And this is a zoom in. You can see quite a lot of interesting fluctuation, isn't it? And this is the second half during the first reaction. A lot of fluctuation and so on. Very, I would say, beautiful. And this is after the trend. You just remove the trend. You apply some media filter and detrend it. And that is the fluctuation you get. Very nice. And now we can visually compare different time frequency representations. This is a spectrogram. This is synchrosqueezing. Okay, before and after. Okay, and you can see some very beautiful, interesting dynamics and curves. And what are they? And this is ConceFT. In the concept, if you compare these two, you will see first it is more concentrated again, and there is a less background strange scenes compared with synchro squeezing. And you can see, okay, this curve, very dominant curve, and so on. And the baseline here is more suppressed. Okay, this is the instantaneous heart rate. How about airflow? You will see before, after. Okay, this is airflow, nothing about EDR. And this is a spectrogram, synchro squeezing. Okay, and this is the concept. So again, if you compare with these two, it is actually sharper and cleaner. And you can catch non-sinusoidal oscillation like everything before. Now, we want to take a look at the instantaneous heart rate and the respiratory signal. This is a respiratory signal. This is instantaneous heart rate. If you pay attention, you will see that, hey, there is a very nice thinning coupling behavior in between the fluctuation in the heart rate and the respiratory signal. And this is the coupling effect, which will be more systematic in the future session. And if you zoom in, you can see there are a lot of coupling. And this coupling can be observed by comparing their time frequency representation. This is the synchro squeezing transform of instantaneous heart rate. You can see these two curves, right? These two curves follow very well. And that is the coupling introduced by the breathing. And yep, this is the concept. The final application will be an application to noxious stimulation, and this is the citation. So the goal is to quantify heart rate variability in the spectral domain so that we can use that spectral domain dynamics to quantify noxious stimulation in the surgery. So the traditional heart rate variability quantification in the spectral domain is very simple. You evaluate the power spectrum and you focus, for example, from 0.04 to 0.15 Hertz. There's a low frequency index or high frequency index over this region. That is okay. But power spectrum, if you think about it, this kind of indices, they actually depend on the stationarity assumption. But in general, this is very non-stationary, so it is maybe not the best idea. So what we can do is we can consider to use the windowing idea. You take a window over this region, evaluate power spectrum and so on. And so that we can evaluate the heart rate variability indices in a time-varying sense. And this is how it works. So you have the signal, you have the short-time Fourier transform, and the spectrogram. And now you can define time-varying heart rate variability indices. For example, this is high frequency region. You evaluate 0.1 Hertz to 1 Hertz, and at fixed time, you integrate over the frequency axis and so on. And this is a low frequency part, or you can evaluate low-high ratio. Okay, very simple. And this is how the signal looks like, how these indices look like. You can see the indices have some fluctuation, not perfect, but well. And I forgot to mention, at time 360 second, the patient was cut. So there was a stimulation, noxious stimulation at this moment. And after noxious stimulation, you can see the heart rate decreases, has a sudden decrease and then increase. This is tachycardia, and this is transient bradycardia. Okay, and this kind of delta wave shaped behavior, the differentiation of delta wave behavior actually is reflected in the time frequency representation here. But it is also masked by the low frequency trend. So you cannot see the dynamics very well, but you can see the high frequency dynamics. There are something, but not very, very strong. Now, this is the concept result. You can see that at this time, the low frequency component is somehow reduced. And you can see a very strong low frequency component associated with the noxious stimulation, transient bradycardia. So you can quantify, this is for a comparison, okay? So you can quantify high frequency and low frequency and the low-high ratio. And this is the dynamics. You can see a very clear and sharp dynamics around stimulation, noxious stimulation. And if you use these indices to quantify noxious stimulation, then you can see something very interesting. Heart rate, which usually we think will be the first response to stimulation, to noxious stimulation, it doesn't work very well. 0.5 is actually like gas. The higher, the better. This is the PK, serial PK index, which I introduced before. I will not discuss it again. And this is a time varying indices, which is okay, can go up to 0.8, but not perfect. However, if you use ConceFT, then this is a red one. You can go up to 0.9 and so on. This is the SSD's ConceFT.